Hello, in this lecture we'll answer two questions. The first question we find out the perimeter of this quadrilateral ABCD, and in the second question we'll find out the area of this green shape. So we start with the first question. In the drawing we have quadrilateral ABCD. You know that line segment BQ equals to 10 units in its length, line segment QP equals to 20 units in its length. This is line segment QC is equals to 4 units in its length. Those three angles are all right angles. Again, our task is to find out the perimeter of this quadrilateral ABCD. What is a perimeter? A perimeter of a quadrilateral is the sum of its four side lengths. In this case, it is AB plus BC plus CD plus DA. So in the first step, we'll do a construction, that is to say, we'll go perpendicular on AD at point P. So actually, this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to our construction. In the next step, we'll extend the perpendicular P from point P until it touches sides BC of this quadrilateral ABCD. And we'll define the touching point of the extended perpendicular from point P and BC. This point is point M. While doing this construction, you're going to do this angle, that is a right angle, and remember, so this is also a right angle. Those two angles are both defined as one-sided internal angles, and the sum of those two right angles is of course 180 degrees. And according to Rule 18, whenever you have the sum of two right angles is equal to 180 degrees, then they must be located between parallel lines. That is to say, those two angles must be located between parallel lines. That is to say, AB is parallel to PM. So please quickly on Rule 18. According to Rule 18, if the sum of two one-sided triangles is equal to 180 degrees, then they lie between parallel lines. They lie between parallel lines. In the drawing, we have those two one-sided triangles alpha and beta. If the sum of those two one-sided triangles is equal to 180 degrees, that is to say, if alpha plus beta equals to 180 degrees, then they are located between parallel lines. That is to say, line A is parallel to line B. So we already implemented Rule 18 in our drawing. Well, because in our drawing, the sum of those two one-sided triangles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, AB is parallel to PM according to Rule 18. If you know, if you found out that side AB is parallel to line segment PM, this is line segment PM, according to Rule 18. Likewise, the sum of those two one-sided triangles is also equal to 180 degrees, and therefore according to Rule 18 they must be located between parallel lines. That is to say, PM is parallel to DC. So you can write down that PM is parallel to side DC of quadrilateral ABCD. Likewise, the sum of those two one-sided triangles is also equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, AB is parallel to DC. Yeah, we have AB is parallel to DC according to Rule 18. So in total, we should find out that those three line segments AB, PD, and DC, they are parallel to each other. Okay, and therefore we can implement here the basic proportionality theorem. Okay, again, we can implement here the basic proportionality theorem. What is the basic proportionality theorem? Here we have AB is parallel to CD and is parallel to DE. We have those two lines, the red lines A and the red line B, connects the three parallel lines together by this third line. A point line A connects the three parallel lines together, and line B also, the red line B also connects the three parallel lines together. And the basic proportionality theorem talks about those two line segments that connect the three parallel lines together by a straight line. The basic proportionality theorem talks about the relation between line A and line B that connects the three parallel lines together. And according to the basic proportionality theorem, AC over CD equals to BD over DE. Again, AC over CD equals to BD over DE. So the basic proportionality theorem talks about those two line segments, those two red line segments A and B that connects the three parallels together. So we can implement the basic proportionality theorem in our drawing. Why? Because in our drawing we have three parallel lines. AB is parallel to PM and it's parallel to DC. And we have, this is side AD that connects the three parallel lines together, and this is side BC that also connects the three parallel lines together. And according to the basic proportionality theorem, the following equation is true: that AP over PD equals to BM over MC. It is also given us the equation that AP equals to PD. So if AP equals to X, then PD must be also equal to X because they are equal to each other according to what is given us the equation. So according to the basic proportionality theorem, the following equation is true. AP over PD is equal to BM over MC. Okay, again, according to the basic proportionality theorem, the following equation is true: that AP over PD equals to BM over MC. AP equals to X and PD also equals to X. So AP over PD is X over X is equals to BM over MC. X over X is 1, so 1 equals to BM over MC. Here we multiply this equation by MC, and we get that MC equals to BM. MC equals to BM. We found out that BM equals to MC. That is to say, point M is the midpoint of BC. Again, point M bisects side BC into two halves. The first half is BM, and it is of course equal to the second half MC, and each half must be equal to BC over 2 because BC is being bisected. So, can I know that the first half of BC is MC, and it is of course equal to the second half of BC, that is BM, and each half must be equal to BC over 2 because BC has been bisected at point M. So BM equals to MC, and each half must be equal to BC over 2. BC in total equals to BQ plus QC. That is to say, BC in total must be equal to 10 plus 40, that is 50. So BC equals to 10 plus 40 over 2. So 10 plus 40 is 50, and 50 over 2 equals to 25. And from this long equation, we will derive that MC equals to BM equals to 25. So she found out that this is 9 segment BM, this is equals to 25 units in its length. Likewise, this is 9 segment MC, that is also equals to 25 units in its length. What is the length of this missing 9 segment? 9 segment QM. From the drawing, it is very easy to see that QM in total equals to BM minus BQ. So write it down. Then she found out that the missing side QM in total is equal to BM minus BQ. So in total QM equals to BM, that is 25, minus BQ, that is 10. 25 minus 10 is 15. So in total we should found out that QM equals to 15 units in its length. This is the missing side QM, is equals to 15 units in its length. So in the next step, we will implement the Pythagoras theorem on this right triangle PQM. I repeat again, we will implement the Pythagoras theorem on this right green triangle PQM. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle BQM, here by PT is the relation from Pythagoras theorem. So in this right green triangle BQM, according to the Pythagoras theorem, we will get that PM squared, that is the square of the hypotenuse, is equal to QM squared plus QP squared. And again, according to the Pythagoras theorem, on this right triangle PQM, the following equation is true. PM squared, that is the square of the hypotenuse, equals to QM squared plus QP squared. PM is the missing side, so we leave it as it is. So it is PM squared equals to QM squared. QM is 15, therefore QM squared is 15 squared, that is 225. Plus QP squared. QP is 20, therefore QP squared is 20 squared, that is 400. So in total we actually found out that PM squared equals to 225 plus 400, that is 625. I repeat again, PM squared equals to 625. Here we will take a root out of this equation, and finally we get that the missing hypotenuse, PM, is equal to the square root of 625, that is 25. So we found out that the length of the hypotenuse PM is equal to 25 units. This is the hypotenuse PM of the right green triangle PQM, and it is equal to 25 units in its length. So write it down here, PM equals to 25 units in its length. In the next step, we will do a construction, that is to say, from point M, we will do perpendicular on DC again. From this point M, we will do perpendicular on DC. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We will define the touching point of the perpendicular from point M and DC. This point is point M. by doing this construction, we created here the small quadrilateral PM and D. Inside this small quadrilateral PM and D, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. According to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral PM and D, we have 4 right angles, and therefore quadrilateral PM and D is a rectangle. In the next step, we'll define angle QPM on this great right triangle QMP. This angle is alpha. So in this right triangle PQM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. BC is one side of quadrilateral ABCD, and therefore it is absolutely a straight line. So if you focus on the left side of the straight line BC at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line BC at point M? We have this angle that is equal to 90 degrees minus alpha, plus this angle that is a right angle, plus this third missing angle. In total, the sum of those 3 angles must be equal to 180 degrees according to rule 3. 90 degrees minus alpha plus 90 degrees is 180 degrees minus alpha. So 180 degrees minus alpha plus the size of this third missing angle, in total must be equal to 180 degrees, and therefore this third missing angle must be equal to alpha. Why? Because 180 degrees minus alpha plus alpha is equal to 180 degrees. That is the sum of the angles on this left side of the straight line BC at point M according to rule 3. Therefore this third missing angle must be equal to alpha. So in the lower right triangle M and C, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that those two right triangles can go into each other according to angle side angle rule. That is to say, we will prove that this green right triangle PQM can go into this right lower triangle MNC according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those are the two hypotenuses of those two right angles. They are both equal to 25, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we actually prove that those two right angles can go into each other according to angle side angle rule. That is to say, we actually prove that those two angles and the side that is included between those two angles, that is side PM, are corresponding equal to those two angles, and the side that is included between those two angles, that is side MC in the right triangle M and C. And therefore those two right triangles can go into each other according to angle side angle rule. So already now we found out that this green right triangle PQM can go in. This is the sign of congruent to this right triangle M and C according to angle side angle rule. Okay, again, we found out that the right main triangle PQM can go into the right lower triangle MNC according to angle side angle rule. And from the fact that those two right main triangles can go into each other, we will derive that those two sides must be also equal to each other according to the rule that said that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding sides must be also equal to each other in their lengths. But PQ equals to 20, therefore the corresponding side MN must be also equal to 20 units in its length according to the rule that I mentioned. So MN must be also equal to 20 units in its length. Likewise, in those two congruent triangles, those two corresponding sides must be also equal to each other in their lengths. But QM is 15, and therefore the corresponding side NC must be also equal to 15 units in its length according to the same rule. So NC must be also equal to 20 units in its length according to the rule that says that corresponding sides and congruent triangles are equal to each other. We already found out that quadrilateral PMND is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PMND, side PM must be equal to the opposite side DN. But PM equals to 25, and therefore the opposite side DN must be also equal to 25 units in its length. Likewise, according to the same rule, in the same rectangle PMND, side MN must be equal to the opposite side PD. PD equals to X and P also equals to X. So MN must be equal to PD. But MN equals to 20, and therefore the opposite side PD equals to X must be also equal to 20 units in its length. PD equals to X, and therefore X equals to 20 units in its length. But AP also equals to X. Therefore AP equals to X, and X equals to 20 units in its length. That is to say, AP also equals to 20 units in its length. So we should found out that side AD in total equals to 20 plus 20, that is 40. This is side DC. In total, side DC equals to 25 plus 15, that is 40. This is side BC. In total, side BC equals to 10 plus 40, that is 50. The only missing side that is left to find is this is side AB. And then we find out the perimeter of this quadrilateral ABCD is equals to AB plus BC plus CD plus DA. So in order to find out the length of side AB, we will implement here the trapezoid mid-segment theorem. First of all, quadrilateral ABCD is a trapezoid. Why? Because we already found out that AB is parallel to DC, AB is parallel to DC. A trapezoid is a quadrilateral with one pair of parallel sides. In quadrilateral ABCD, side AB is parallel to side DC, and therefore quadrilateral ABCD is a trapezoid. In trapezoid ABCD, the two parallel sides AB and CD are defined as the bases of the trapezoid, while the two other sides that are not parallel to each other, that is to say AD and BC, are defined as the legs of this trapezoid. Okay. Actually, trapezoid mid-segment theorem talks about the length of line 7 PM. This is line 7 PM. Line 7 PM bisects the leg AD. Why line 7 MP bisects leg AD? Because at point P, AD is being bisected into two halves. Each half equals to 20. AP equals to 20, and PED also equals to 20. Likewise, line 7 PM bisects side BC. Why? Because it's point M. Point M is the midpoint of BC. That is to say, at point M, BC is being bisected into two halves. The first half BM is 25. The second half is MC, that is also 25. So in conclusion, we found out that line 7 PM bisects both legs, the legs AD, and bisects the legs BC. And therefore, line 7 PM is defined as the mid-segment of this trapezoid ABCD because of the fact that it bisects the two legs AD and BC. Trapezoid mid-segment theorem talks about the length of the mid-segment PM. According to the trapezoid mid-segment theorem, PM equals to the sum of its two parallel bases over 2. That is to say, PM equals to AB plus DC over 2. So maintenant, we found out that according to the trapezoid mid-segment theorem, the mid-segment PM, the length of the mid-segment PM that bisects the two legs AD and BC, PM equals to the sum of the two parallel bases of trapezoid ABCD, that is actually AB plus DC, divided by 2. We already found out that PM equals to 25, so we'll substitute PM by 25. That is the mid-segment of trapezoid ABCD, and it is equals to AB. AB is the missing side, so we'll leave it as it is. So it is AB plus DC. DC in total equals to DN, that is 25, plus NC, that is 15. So DC in total equals to 25 plus 15, that is 40. So we'll substitute DC by 40. Divided by 2. So in total, we found out that 25 equals to AB plus 40 over 2. Here we will multiply this equation by 2 and finally get that 25 times 2 is 50, and 50 equals to AB plus 40. Here we will subtract 40 from this equation and finally get that the missing side AB is equal to 50 minus 40, that is 10. So AB equals to 10 units in its length. This is side AB is equals to 10 units in its length. Therefore, the perimeter of this trapezoid ABCD is equals to the sum of its two, the sum of its four line side lengths. That is to say, the perimeter of quadrilateral ABCD or trapezoid ABCD in total it must be equal to AB, that is 10, plus AD, that is 20, plus 20, that is 40, plus DC in total equals to 25 plus 15, that is also 40, plus BC in total equals to 10 plus 40, that is 50. So in total we should find out that the perimeter of quadrilateral ABCD, is actually trapezoid ABCD, in total it equals to 40 plus 40 is 80, 80 plus 10 is 90, and 90 plus 50 is 140 units. So the answer to the question is that the perimeter of this quadrilateral ABCD is equal to 140 units in its length. In the next step, I will present to you a second method to find out that AB equals to 10 units in its length. According to the first method, we found out that AB equals to 10 units in its length by implementing the trapezoid mid-segment theorem on our drawing. In the second method, we do it in another way, that is to say, from point B we will draw perpendicular on PM. Again, from point B, we will draw perpendicular on PM, on the mid-segment PM. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point B in PM. This point is point S. By doing this construction, we can do quadrilateral ABSP. In quadrilateral ABSP, we have 1, 2 rectangles, and therefore this fourth angle must be equal to 90 degrees in each side. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So quadrilateral ABSP is 4 rectangles, and therefore it is a rectangle. The small quadrilateral ABPS is a rectangle. It is very easy to see that those two right angles can go into each other according to angle side angle rule. That is to say that this right angle BSM, the upper right angle BSM, can go into the lower right angle MNC according to angle side angle rule. That is to say, but before that, in triangle BSM, this angle equals to 90 degrees minus alpha. This angle equals to 90 degrees, and therefore this first angle must be equal to alpha. Well, because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So why those two right angles can go into each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two hypotenuses of those two right angles are both equal to 25, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if we found out that those two right angles can go into each other according to angle side angle rule. That is to say, we actually proved that those two angles and the side that is included between those two angles, that is side VM, in this right angle BSM, are corresponding equal to those two angles, and the side that is included between those two angles, that is side MC, this right angle MNC. And therefore those two right angles can go into each other according to angle side angle rule. So I write it down. Actually prove that the right angle BSM, the upper right angle BSM, can go into the lower right angle MNC according to angle side angle rule. Okay, again, we should find out that the upper right angle BSM can go into the lower right angle MNC according to angle side angle rule. And from the fact that those two right angles can go into each other, we will derive that those two corresponding sides must be also equal to each other in their lengths, according to the sum rule that says that corresponding sides that can go into angles are equal to each other. So NC equals to SM, but NC is 15, therefore SM must be also equal to 15 units in its length. So SM equals to 15 units in its length. So what is the length of the missing line segment PS? From drawing it is very easy to see that PS in total equals to PM minus SM. So the norm, PS in total equals to PM minus SM. So PS in total, this is the missing side PS, in total it must be equal to PM, that is 25, it is the mid segment of trapezoid ABCD, it is equals to 25 minus SM. We just right now found out that SM equals to 15. So in total PS equals to 25 minus 15, that is 10. PS equals to 10 units in its length. This is the missing side PS, and this is equal to 10 units in its length. So in rectangle AB SP, side AB must be equal to the opposite side SP. But SP is 10, therefore the opposite side AB must be also equal to 10 units in its length. We should find out in the Second method, that AB must be equal to 10 units in its length. And the answer to the question is that the perimeter of this quadrilateral ABCD is equal to 140 units in its length. So we finished to answer the first question. In the next step, I present you the second question, and we'll answer the second question of this lecture. In the second question, our task is to find out the area of this green shape. So in the drawing, we have two semicircles. This is the big semicircle. Inside this big semicircle, we have this small semicircle. So the big semicircle contains this small semicircle. We also know that this is line segment AC, this equals to 4 units in its length. This is line segment CB, this equals to 6 units in its length. Again, our task is to find out the area of this green shape. First of all, we will define the center of this big semicircle. This point is point O. Likewise, we will define the center of this small semicircle. This point is point S. In the next step, we find out the radius of this big semicircle. The diameter of this big semicircle is AB. AB in total equals to AC, that is 4, plus CB, that is 6. So in total, AB equals to 4 plus 6, that is 10. And the radius must be equal to half of the diameter. We define the radius of this big semicircle as R. So the radius R of this big semicircle must be equal to the diameter AB over 2. AB in total is 6 plus 4 over 2. 6 plus 4 is 10, and 10 over 2 is 5. So we found out that the radius R of the big semicircle equals to 5 units in its length. So actually, the radius OB of this big semicircle equals to 5. And the radius OA also equals to 5 units in its length of the big semicircle. In the next step, actually, the touching point between the big semicircle and the small semicircle is defined as point P, and this is point Q, according to what is given as the question. In the next step, we will define the radius of this small semicircle as x. So the radius SQ equals to x, and the radius SP of this small semicircle also equals to x. In the next step, we will join points S and C together by straight line. Point C is the point of tendency of tangent AB with this small semicircle. So we join points S and C together by a straight line. So what is the definition of line segment SC? Line segment SC starts from point S, that is the center of this small semicircle, and ends at point C, that is the point of the small semicircle itself. So this is exactly the definition of the radius. Therefore, SC is the radius of this small semicircle, is equals to x units in its length according to our definition. So here we can implement rule 1. Why? Because the radius SC that is equals to x, the radius SC of this small semicircle that is equals to x is drawn to point C, that is the point of tendency of tangent AB with this small semicircle. And whenever you have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the reduced CS. If AB is perpendicular to CS, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we will do another construction. That is to say, from point P, we will draw perpendicular on AB. Again, from point P, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees in its size. And this angle also equals to 90 degrees in its size according to our construction. And we define the touching point of the perpendicular from point P and AB. This point is point M. What is the definition of line segment MP? Line segment MP is tangent to this semicircle at point P. Therefore, MP is a tangent. MP is a tangent. So we have here the radius SP of this small semicircle that is equals to x. The radius SP is going to point P, that is the point of tendency of tangent MP with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent MP will be perpendicular to the radius PM. If MP is perpendicular to PM, it means that this angle equals to 90 degrees in its size, and this angle also equals to 90, and this angle equals to 90 degrees in its size. According to rule 1, of course. So in total, in the small quadrilateral PSCM, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be equal to 90 degrees in its size, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral PSMC, we have 4 rectangles, and therefore we can relate to quadrilateral PSMC as a rectangle. Because it has 4 rectangles. But we also know that the opposite sides of the rectangle are equal to each other. So in the small rectangle PSCM, side SC must be equal to the opposite side PM. But SC is x, therefore the opposite side PM must be also equal to x units in its length. Likewise, according to the same rule, in the same rectangle PSCM, side PS must be equal to the opposite side MC. But PS is x, therefore the opposite side MC must be also equal to x units in its length. So in total, we should find out that quadrilateral PSCM is not a rectangle but a square, but because all of its sides are equal to each other, its side equals to x. So quadrilateral PSCM is a square. In the next step, we will do a construction, that is to say, we will complete this semicircle, this big semicircle, to a circle. So I completed the semicircle to a circle. In the next step, we will extend the tangent PM by side line until it touches the circle. And we will define the touching point of the extended tangent PM with this circle. This point is point N. So by doing this construction, we get here chord PN. This is chord PN. PM is a tangent. PM is a tangent, it is absolutely a straight line. And when you extend a straight line by straight line, the result PN must be also a straight line. So PN, it is definitely a straight line. PN is actually a straight line because PN is a chord. Okay? So if you focus on right side of the straight line PN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line PN at point M? We have this angle, the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the drawing, we have here, this is perpendicular OM on chord PM. Again, this is perpendicular OM on chord PN. Why OM is a perpendicular? Because this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 3. Therefore, we have here from the center of this big semicircle or from the center of this big circle, we have perpendicular OM on chord PN. And according to rule 15, a perpendicular that is drawn from the center of the circle towards any chord will bisect the chord. So if it's quickly on rule 15, according to rule 15, a perpendicular from the center of a circle towards any chord bisect the chord. So in the drawing, we have a circle. Point S is the center of the circle. From the center of this circle, that is to say from this point S, we have perpendicular ST on chord MN. And according to this rule, rule 15, perpendicular ST bisect chord MN. That is to say, at point T, MN, chord MN has been bisected into two halves. The first half is MT, and it is definitely equals to the second half TN. Each half must be equal to Mn over 2, because Mn has been bisected at point T. So again, according to rule 15, perpendicular ST bisects chord Mn. That is to say, the first half Mt equals to the second half Tn, and each half must be equal to Mn over 2, because Mn has been bisected. Mt equals to Tn equals to Mn over 2. So we can implement rule 15 in our drawing. Because in our drawing, this is perpendicular OM from the center of the circle, that is to say from point O, we have perpendicular OM on chord PN. And according to rule 15, perpendicular OM bisects chord PN. That is to say, PN has been bisected into two halves, according to rule 15, by perpendicular OM. That is to say, the first half is PM, and is equal to the second half MN. So according to rule 15, perpendicular OM bisect chord PM. That is to say, the first half of PM must be equal to the second half of PM, that is MN. And again, perpendicular OM bisect chord PN. That is to say, the first half PM must be equal to the second half MN. But we already found out that PM equals to X. We can write here that PM equals to X. And from this equation, X equals to PM equals to MN. We will derive that Mn must be also equal to X units in its length. Mn equals to X units in its length. This is 9/7 Mn is equals to X units in its length. In the next step, we will implement rule 24 in our drawing. So I'll repeat quickly on rule 24. According to rule 24, first of all, rule 24 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. That AO times BO equals to CO times DO. So in the moment we have a circle. This is called AB that intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. So whenever you have two chords that intersect with each other in any circle, the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can definitely implement rule 24 in our drawing. Why? Because in our drawing we have here, this is called AB. This is actually the diameter of this big circle. So chord AB intersects with chord PN at point M. Again, chord AB intersects with chord PN at point M. So all the requirements for rule 24 are satisfied, and therefore we can implement here rule 24. So write it down. So now original drawing, we have chord AB, the diameter of the circle, of the big circle, intersects with chord PN at point M. This is the intersection point. And again, in our original drawing, we have chord AB that intersects with chord PN at point M. So all the requirements of rule 25 or rule 24 are satisfied, and therefore we can implement rule 24. According to rule 24, the following equation is true. That AM times MB, AM times MB is equal to PM times MN. PM times MN. And again, according to rule 24, the following equation is true. That AM times MB equals to PM times MN. This equation is the implementation of rule 24 in our drawing. But first of all, we will find out the length of this short line segment AM. What is the length of AM? From the drawing it is very easy to see that AM in total equals to AC minus MC. Again, AC minus MC equals to AM. So write it down. If we found out that the short line segment AM in total it is equals to AC minus MC. So AM in total equals to AC, that is 4, minus MC, that is X. So in total, we found out that AM equals to 4 minus X units in its length. This is the short line segment AM, that is equals to 4 minus X units in its length. So in this equation, we substitute AM by 4 minus X times MB. What is the length of this line segment MB? MB in total equals to X plus 6. It's very easy to see from the drawing that MB equals to MC, that is X, plus CB, that is 6. So in total, MB equals to X plus 6 units in its length. So we substitute MB by X plus 6. So in total, on this side of the equation, we have 4 minus X times X plus 6. And it equals to PM, PM is X, times MN, that is also X. X times X is X squared. So in total, we found out that 4 minus X times X plus 6 equals to X squared. So here we open the brackets on this side of this equation, and finally we get that 4 times X is 4X. 4 times 6 is 24, so it is plus 24. Minus X times X is minus X squared. And we have minus X plus 6, that is minus 6X, equals to X squared. So in this side of the equation, we have 4x minus 6x is minus 2x. We have plus 24 minus x squared equals to x squared. So in total we found out that minus 2x plus 24 minus x squared equals to x squared. Here we will add x squared to this equation, and finally we get that minus 2x plus 24 equals to x squared plus x squared is 2x squared. Here we add 2x to this equation, and you get that 24 equals to 2x squared plus 2x. And again we found out in total that (24) equals to 2x squared plus 2x. Here we will subtract 24 from this equation, and finally get that in this side of the equation we have nothing, that is to say 0, while on the other side of the equation we have 2x squared plus 2x minus 24. So total 2x squared plus 2x minus 24 equals to 0. Here we divide this equation by 2, and finally we get that 2x squared over 2 is x squared, plus 2x over 2 is x, minus 24 over 2 is minus 12, equals to 0 over 2 is 0. So in total we should find out that x squared plus x minus 12 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula, capital A, capital B, and capital C are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula. X equals to minus b plus minus the square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus x minus 12 equals to 0, the variable that we are looking for is x. X is the radius of this small semicircle, so written on, x is the radius of the small semicircle. The coefficient a equals to 1, our specific quadratic equation. The coefficient b also equals to 1, and the coefficient c equals to minus 12. So the only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x. In this way we find out the value of the values of x, because we might have two answers for the value of x. Okay, so we'll do it now. We'll put the data of our specific quadratic equation inside this general formula for x in order to find out the radius of the small semicircle that is x. So according to the general formula, x equals to minus b. B is 1, so minus b is minus 1, plus minus square root of b squared. B is 1, so b squared is 1 squared, that is 1, minus 4 times a times c. Minus 4 times a is 1, so minus 4 times 1 is minus 4 times c. C is minus 12, so minus 4 times minus 12 is plus 48. So in total, minus 4 times a times c equals to plus 48 over 2a. Over 2a. Here we have 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, we actually found out that x equals to minus 1 plus minus, inside the root we have 48 plus 1 is 49 over 2. So in total, x equals to minus 1 plus minus, the square root of 49 is 7 over 2. And again, we found out that In total, x equals to -1 plus -7 over 2. So here we will have two solutions for x. The first solution for x is x equals to -1 -7 over 2. -1 -7 is -8, and -8 over 2 is -4. So according to the first solution for x equals to -4. But x is the radius of this small semicircle. That is to say, x is a length. So x as a length, it must be a positive number. So -4 can never be equal to x. It is a negative number. X must be a positive number. So we cancel this first solution for x, and we'll take into account only the second solution for x. The second solution for x is that x equals to -1 plus 7 over 2. Again, x equals to -1 plus 7 over 2. -1 plus 7 is 6, and 6 over 2 is 3. So the second solution for x is that x equals to 3 units in its length. This is to say, the radius of this small semicircle x equals to 3 units. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total must be equal to the area of this big semicircle minus the area of this small semicircle. So now if you found out that the area of the green shape in total must be equal to the area of the big semicircle, we only found out that the radius of the big semicircle equals to 5 minus the area of the small semicircle. Minus the area of the small semicircle, we already found out that the radius of the small semicircle equals to 3. So the area of the green shape in total must be equal to the area of the big semicircle. The radius of the big semicircle is 5. The area of the semicircle must be equal to pi r squared over 2. R is 5, so it is pi times 5 squared over 2. Likewise, the area of the minus the area of the small semicircle. So the radius of the small semicircle is 3, therefore the area of the small semicircle must be equal to pi times the radius squared, that is 3 squared over 2. So in total, pi, in the numerator of this expression we have 5 squared, that is 25, so in total in the numerator of this expression we have 25 pi over 2. Here in the numerator of this expression we have 3 squared, that is 9, so in total we have 9 minus 9 pi over 2. 25 pi minus 9 pi is 16 pi over 2. 16 pi over 2 is 8 pi. 8 pi, in terms of numbers, is equal to 25.13 units in its length. And again, the green shape in total is equal to either 8 pi square units in its size. In terms of numbers, it is equal to 25.13 square units in its size. Repeat again. The area of this green shape, that is the area that we are looking for in this question, is equal to either 8 pi square units in its size, or in terms of numbers, it is equal to 25.13 square units in its size. So we finished to answer on the second question. In the next step, I will summarize the lecture. We start with the repetition of the first question. and then repeat on the solution of this second question. In the first question, our task was to find out the area of this quadrangle ABCD. So in the drawing, we have the big quadrangle ABCD. This is line segment BQ, is equals to 20 units in its length. This is line segment QC, this is equals to 40 units in its length. This is line segment PQ, this is equals to 20 units in its length. Those three angles are both right angles. Again, our task is to find out the perimeter of this quadrangle ABCD. What is the perimeter? The perimeter of any quadrangle is equal to the sum of its four side lengths. In this case, it is AB plus BC plus CD plus DA. So our task is to find out the perimeter of this quadrangle ABCD. So in the next step, we did a construction, that is to say, we drew perpendicular on AD at point P. Again, we drew perpendicular on AD at point P. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. In the next step, we extended the perpendicular from point P until it touches side BC of this quadrangle ABCD. And we find the touching point of the perpendicular from point P and side BC. This point is point M. By doing this construction, we created this angle, that is a right angle. This right angle is defined as one-sided in two angles. Those two angles are both defined as one-sided in two angles. The sum of those two one-sided angles is equal to 180 degrees. And therefore, according to Rule 18, whenever we have the sum of two one-sided triangles is equal to 180 degrees, then they must be located between parallel lines. That is to say, those two angles must be located between parallel lines. This means that side AB must be parallel to side PM. So repeat quickly on Rule 18. According to Rule 18, if the sum of two one-sided triangles is equal to 180 degrees, then they must be located between parallel lines. So in the drawing, we have those two angles are both defined as one-sided angles. So if the sum of those two one-sided angles is equal to 180 degrees, that is to say if alpha plus beta equals to 180 degrees, then those two one-sided angles must be located between parallel lines. That is to say, line A is parallel to line B. We have already implemented Rule 18 in our drawing. Why? Because in our drawing, the sum of those two one-sided angles is of course equals to 180 degrees, and therefore they must be located between parallel lines. That is to say, AB is parallel to PM. Again, AB is parallel to PM according to Rule 18. Likewise, the sum of those two one-sided angles is also equals to 180 degrees, and therefore they must be located between parallel lines. That is to say, PM is parallel to DN. PM is parallel to DC because DC is one straight line. Okay, so PM is parallel to DC. PM is parallel to DC according to the same Rule 18. Likewise, the sum of those two one-sided integrals is also equals to 180 degrees, and therefore they must be located between parallel lines. That is to say, side AB is parallel to side DC. Again, AB is parallel to DC according to the sum rule, rule 18. So in total, we found out that all the three line segments AB and PM and DC, they are parallel to each other according to rule 18. Those three parallel lines AB, PM and DC, they are connected by AD and by BC. They are connected together by AD, by line segment AD, and by line segment BC. And now you have three or more parallel lines that are located, that are connected together by other two line segments that are not parallel to each other. You can implement the basic proportionality theorem. According to the basic proportionality theorem, the following relationship exists between AD and BC that connects the three parallel lines together. The relationship is as follows: AP over PD equals to BM over MC. Again, according to the basic proportionality theorem, the following relationship exists between AD and BC, the two line segments that connect the three parallel lines together by a straight line. AP over PD equals to BM over MC. AP over PD equals to BM over MC. This is given us the equation that AP equals to PD. So we define FP as X, and PD must be also equal to X because they are equal to each other according to what is given us the equation. So we can substitute AP by X and PD by X, and it equals to BM over MC. X over X is 1, so 1 equals to BM times MC. Here we multiply this equation by MC and finally found out that MC equals to BM. This is to say BM equals to MC. So at point M, side BC is being bisected into two halves. The first half is BM, and this equals to the second half, that is MC. Each half must be equal to BC over 2 because BC has been bisected into two halves. So the first half of BC is equal to MC, and it is of course equal to the second half of BC, that is BM. Each half must be equal to BC over 2 because BC has been bisected into two halves. But BC in total, this is side BC in total, it is equals to BQ, that is 10, plus QC, that is 40. So in total, BC equals to 10 plus 40. So BC in total equals to 10 plus 40 over 2. 10 plus 40 is 50, and 50 over 2 is 25. From this long equation, we will derive that MC equals to BM equals to 25. MC equals to BM equals to 25. That is to say, BM equals to 25 units in its length, and MC must, it is also equals to 25 units in its length. In the next step, we did another construction, that is to say, from point M, we do perpendicular on DC. Again, from point M, we do perpendicular on DC. So actually, this angle equals to 90 degrees in its size, and this angle must be also equal to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point M and side DC. This point is point N. By doing this construction, we can derive quadrangle PM and D. Inside quadrangle PM and D, we have 1, 2, 3 right angles. The sum of three right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle in total must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrangle PM and D we have 4 right angles, and therefore quadrangle PM and D is a right angle because it has 4 right angles. In the next step, we just right now found out that BM equals to 25. BQ equals to 10 according to what is given us the question. So QM in total must be equal to BM must BQ. Okay. QM equals to BM must BQ. So QM in total equals to BM, that is 25, must BQ, that is 10. So QM in total equals to 25 minus 10, that is 15. So QM equals to 15 units in its length. In the next step, we implemented the Pythagoras theorem of this right triangle PQM. according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right again triangle PQM, PM squared, that is the square of the hypotenuse, equals to PQ squared plus QM squared. Repeat again, this right triangle PQM, the right again triangle PQM, according to the Pythagoras theorem, PM squared, that is the square of the hypotenuse, equals to QM squared plus QP squared. PM is the missing hypotenuse, so we leave it as it is. So it is PM squared equals to QM squared. QM is 15, therefore QM squared is 15 squared, that is 225, plus QP squared. QP is 20, therefore QP squared is 20 squared, that is 400. So in total, we can find out that PM squared equals to 225 plus 400. Again, we found out that PM squared equals to 225 plus 400. 225 plus 400 is 625. So in total, we found out that PM squared equals to 625. Here we took out of this equation, if we found out that the missing hypotenuse PM is equal to the square root of 625, that is 25. So the rest of the hypotenuse PM is equal to 25 units. In the next step, we define this angle QPM is alpha. So, but before that, so this angle equals to alpha, and this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in any triangle. So this first angle must be equal to 90 degrees minus alpha. BC is one side of quadrilateral ABCD. So BC is one side of a quadrilateral, it is absolutely a straight line. So if you focus on the left side of the straight line, BC is point M. Here the sum of the angles must be equal to 180 degrees, according to all three. All three said that the sum of the angles in any quadrilateral is the sum of the angles on one side of the straight line is equal to 180 degrees. But before that, in quadrilateral PM and D, we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees inside, according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth angle must be equal to 90 degrees inside. So quadrilateral PM and D is 4 angles, and therefore it is a rectangle. So in the right side of the straight line BC is point M, the sum of the angles must be equal to 180 degrees according to all three. Again, all three said that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the left? On the left side of the straight line BC is point M. We have this angle that is equal to 90 degrees minus alpha, plus this angle that is right angle, plus this third angle. In total must be equal to 180 degrees according to all three. So 90 degrees minus alpha plus 90 degrees is 180 degrees minus alpha, plus the missing angle in total must be equal to 180 degrees according to all three. Therefore this first missing angle must be equal to alpha. Why? Because 180 degrees minus alpha plus alpha is 180 degrees. That is the sum of the angles on the left side of the straight line BC at point M, according to all three. Therefore this first missing angle must be equal to alpha. So in the right lower triangle MNC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha according to the sum rule that said that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. In the next step, we prove that those two right angles can go into each other according to angle sine angle rule. Why those two right angles can go into each other? That is to say, we prove that this right hand triangle PQM can go into this right lower triangle MNC according to angle sine angle rule. That is to say, we actually prove that those two angles, that is to say, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, the hypotenuse PM of this grand triangle equals to the hypotenuse MC of this right triangle MNC. So both hypotenuses that are both equal to 25, and therefore they are equal to each other. And finally, those two angles that are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we actually prove that those two right angles can go into each other according to angle side angle rule. That is to say, we actually prove that those two angles and the side that is included between those two angles, that is side PM, and this right angle PQM, are corresponding equal to those two angles, and the side that is included between those two angles, that is side MC, this right angle MNC. Therefore, those two right angles can go into each other according to angle side angle rule. Repeat again, we should find out in total that the green right angle PQM can go to the right angle MNC according to angle side angle rule. And from the fact that those two right angles can go into each other, we have that those two sides are also equal to each other in their lengths. That is to say, we grab that those two sides must be also equal to each other in their lengths. That is to say, side PQ of this rectangle, PQM, is equal to side MN of this right angle MNC. But PQ is 20, therefore MC must be also equal to 20, according to the rule that states that corresponding sides in congruent angles are equal to each other. Those two right angles can go into each other, therefore those two corresponding sides must be also equal to each other in their lengths. But PQ is 20, therefore MN must be also equal to 20 units in its length. Likewise, from the fact that those two right angles can go into each other, we derive that those two corresponding sides must be also equal to each other in their lengths. But QM is 15, and therefore the corresponding side NC must be also equal to 15 units in its length. So in total, side DC equals to 25 plus 15, that is 40. We know that PM equals to 25, AB is the missing side. This is quadrangle ABCD. Quadrangle ABCD is a trapezoid because of the fact that side AB is parallel to side DC. According to Rule 18, side AB is parallel to side DC. And the definition of a quadrangle, definition of a trapezoid is a quadrangle with one pair of parallel sides. In quadrangle ABCD, side AB is parallel to the opposite side DC, and therefore quadrangle ABCD is a trapezoid. So in trapezoid ABCD, side AB and side DC are defined as the bases of the trapezoid, while AD and BC, the two sides that are not parallel to each other, are defined as the legs of trapezoid ABCD. What is the definition of PM? PM is the mid-segment of trapezoid ABCD. That is to say, 7 PM bisect the leg AD. Why? Because at point P is the midpoint of AD. And at point P, side AD is being bisected into two halves. The first half AP is X, equals to the second half PD, this is also X. Likewise, the same mid-segment PM bisect also the leg BC. At point M, the leg BC has been bisected into two halves. The first half is BM, and it is equal to the second half MC. Each half equals to 25 units. So, PM bisects both legs, AD and BC. And according to the trapezoid mid-segment theorem, the length of side PM equals to the sum of its two parallel bases, that is to say AB plus DC over 2. Again, the length of the mid-segment PM is equal to the sum of its two parallel bases, that is actually AB plus DC over 2. And again, according to the trapezoid mid-segment theorem, the length of mid-segment PM is equal to the sum of its two parallel bases, that is to say it is equal to AB plus DC over 2. AB is the missing side, so we leave it as it is, plus DC. DC in total equals to 25 plus 15, that is 40. AB is the missing side, DC equals to 40, divided by 2. So in total we found out PM is 25 according to what we have only found out. So we substitute PM by 25 and it equals to AB. AB is the missing side plus DC is 40 over 2. Here we multiply this equation by 2 and finally found out that 25 times 2 is 50. So 50 equals to AB plus 40. Here we subtract 40 from this equation and finally found out that AB equals to 50 minus 40, this is 10. So if you found out the missing side AB equals to 10 units in its length. The perimeter of trapezoid ABCD or quadrangle ABCD is equals to AB plus DC, AB plus AD plus DC plus CB. That is the sum of the sum of the four sides lengths of quadrangle ABCD. AB is 10 plus AD. So we have to do another rules here in order to find out the final answer, that is the perimeter of this quadrangle ABCD. So we have here in quadrangle PM and D, we already found out that quadrangle PM and D is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, PM equals to the opposite side DN. But PM is 25, therefore the opposite side DN is also 25. Likewise, according to the same rule in the same rectangle PM and D, side MN must be equal to the opposite side PD. But MN is 20, therefore the opposite side PD must be also equal to 20. X equals to 20. So here AP must be also equal to 20 because AP equals to PD. So AP equals to PD, each side equals to 20. So in total we found out that the perimeter of this quadrangle ABCD equals to AB, that is 10, plus AD, that is 40, 20 plus 40 is 50, plus DC, that is 40, and 50 plus 40 is 90, plus BC, that is 50, 90 plus 50 is 140. Again, the perimeter of quadrangle ABCD equals to AB, that is 10, plus AD, that is 40, plus DC, that is also 40, plus BC, that is 50. 10 plus 40 plus 40 plus 50 equals to 140 units in its length. The perimeter of this quadrangle ABCD equals to 140 units in its length. In the next step, I presented to you the second method, how to find out the length of side AB. According to the first method, we only found out that AB equals to 10 units. So, in the next step, I presented to you a second method that will help us to find out the length of side AB. According to the first method, we implemented the trapezoid mid-segment theorem in order to find out that AB equals to 10. In the second method, we did the construction, that is to say, from point B we drew perpendicular on PM. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and PM, this point is point S. By doing this construction, we can do quadrangle ABSP. Inside quadrangle ABSP, we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees inside. So in quadrangle ABSP, we have 4 angles, and therefore quadrangle ABSP is a rectangle. So in this right angle BSM, this angle equals to 90 degrees minus alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to alpha, according to the rule that said that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we prove that those two right angles can go into each other according to angle side angle rule. That is to say, we prove that this the right angle BSM can go into this right angle, the right angle M and C according to angle side angle rule. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, the hypotenuses of those two right angles are both equal to 25 and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. Therefore, those two right angles can go into each other according to angle side angle rule. That is to say, we actually found out that those two angles and the side that included between those two angles, that is side VM, in this right angle BSM corresponding equal to those two angles, and the side that is included between those two angles, that is side MC, this right angle MNC. And therefore those two right angles can go into each other according to angle side angle rule. But again, we should find out that the upper right angle BSM can go into the lower right angle MNC according to angle side angle rule. And from the fact that those two right angles can go into each other, we will derive that the two corresponding sides are also equal to each other. That is to say, side SM, this right angle BSM, is equal to the corresponding side NC on this right angle MNC. According to the rule that corresponding sides that can go into triangles are equal to each other, those two triangles can go into each other, therefore those two corresponding sides, that is to say, SM and NC, must be also equal to each other in their lengths. But we already found out that NC equals to 15, and therefore the corresponding side SM must be also equal to 15 units in its length. So what is the length of the missing line 7 PM? PS. PS equals to PM minus SM. Again, PS equals to PM minus SM. So PS in total equals to PM, that is 25, minus SM, that is 15. So in total PS equals to 25 minus 15, that is 10. So in rectangle ABSP, side PS must be equal to the opposite side AB. But PS is 10, therefore the opposite side AB must be also equal to 10 units in its length. So this way actually represented to a second method to find out that AB equals to 10 units in its length. According to, in the first method, we relied on the trapezoid segment theorem in order to find out that AB equals to 10, when in this second method we found out that AB equals to 10 by doing the construction and by proving that those two right angles can go into each other according to angle side angle rule. So in total we found out that the perimeter of this quadrilateral, quadrilateral ABCD is equal to 140 units in its length. So we finished. So repeat on the first question. In the next step, I repeat on the solution of the second question. In the second question, our task is to find out the area of this green shape. So in the drawing, we have two semicircles. This is the big semicircle. Inside the big semicircle, we have this small semicircle. In addition, we know that this is line segment AC, that is equals to 4 units in its length. This is line segment CB, that is equals to 6 units in its length. Again, our task is to find out the area of this green shape. In the first step, we define the center of this big semicircle, this point as point O. We define the center of this small semicircle, this point as point S. AB is the diameter of this big semicircle. AB in total equals to AC, that is 4, plus CB, that is 6. So AB in total equals to 4 plus 6, that is 10. So the diameter AB of the big semicircle equals to 6 plus 4, that is 10. And therefore the radius must be equal to half of it. That is to say, the radius R of the big semicircle must be equal to the diameter AB over 2. That is to say, it must be equal to 10 over 2, that is 5. So in total, if you remember that the radius of this big semicircle R equals to 5 units in its length. In the next step, we define the radius of this, so the radius of the big semicircle equals to 5 units in its length. We define the radius of this small semicircle as x. So the radius SP equals to x, the radius SQ of this small semicircle also equals to x. In the next step, we join points S and C together by a straight line. What is the definition of line segment SC? Line segment SC starts from point S, that is the center of this small semicircle, and that's at point C, that is the point of the small semicircle itself. So this is exactly the definition of a radius. So SC is the radius of this small semicircle, is equals to x according to our definition. Here we can implement rule 1, right, because we have the radius SC that is equals to x. The radius SC is going to point C, that is the point of tendency AB with this small semicircle. And whenever you have a radius that is down to the point of tendency, then AB will be perpendicular to the radius CS. If AB is perpendicular to CS, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did another construction, that is to say from point P, that is the touching point between the small semicircle and the big semicircle. From point P, we go perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and AB. This point is point M. And in the next step, we found out that AM in total equals to AC minus MC. So AM equals to AC, that is 4 minus MC. So first of all, we have to find out that this quadrilateral is a square. So by doing this construction, we can do the quadrilateral PMCS. But what is the definition of PM? PM is a tangent, or MP is a tangent to this small semicircle at point P. So here the radius SP is equals to x. The radius SP is drawn to point P, that is the point of tendency of tangent MP with this small semicircle. And whenever you have radius that is drawn to the point of tendency, then tangent MP will be perpendicular to the radius PS. If MP is perpendicular to PS, this means that this angle equals to 90 degrees according to rule 1. So in total, in the small quadrilateral PSCM, we have 1, 2, 3 right angles, and therefore this fourth missing angle must be equal to 90 degrees in its size according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore in the small quadrilateral PSCM we have 4 right angles, and therefore quadrilateral PS we can relate to quadrilateral PSCM as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle PSCM, side PS must be equal to the opposite side MC. But PS equals to x, therefore the opposite side MC must be also equal to x units in its length. Likewise, according to the sum rule, in the same small rectangle PSCM, side SC must be equal to the opposite side PM. But SC is x, therefore the opposite side PM must be also equal to x units in its length. So in total, we found out that quadrilateral PSCM is not a rectangle but a square, because of the fact that all of its sides are equal to each other, each side equals to x. So the small quadrilateral PSCM is a square. In the next step, we did a construction. That is to say, we completed this big semicircle to a circle, and then we extended PM by straight line until it touches the circle. We define the starting point of the extended tangent PM with this circle. This point is point N. PM is a tangent. PM is a tangent. It is absolutely a straight line. When you extend the straight line by straight line, the result Pn is also a straight line. So if you focus on the right side of the straight line Pn, it's point M. Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 said that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line Pn at point M? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the drawing, we have from the center of this big circle, we have perpendicular OM on chord Pn. Again, we have here perpendicular OM on chord Pn. And according to rule 15, a perpendicular that is drawn from the center of the circle towards any chord bisects the chord. So I click on rule 15. According to rule 15, a perpendicular from the center of a circle towards any chord bisect the chord. In the drawing we have a circle. Point S is the center of the circle. So from point S we have perpendicular ST on chord MN. And according to this rule 15, perpendicular ST bisects chord MN. If ST bisects chord MN, it means that the first half of MN is empty, and is definitely equals to the second half of MN, that is 10. Each half must be equal to MN over 2 because MN has been bisected by ST. So MT equals to Tn equals to Mn over 2. You can definitely implement rule 15 in our drawing. Why? Because in our drawing we have from the center of this big circle, that is to say from point O, we have perpendicular OM on chord Pn. And according to rule 15, perpendicular OM bisects chord Pn. That is to say, it divides chord Pn into two halves. The first half Pm equals to the second half Mn. Each half must be equal to Pn over 2. So according to rule 15, perpendicular OM bisects chord Pn. The first half of Pn is Pm, and it is of course equals to the second half of P. It is of course equals to the second half of Pn, that is Mn. So the first half of Pn, that is Pm, equals to the second half of Pn, that is Mn. And each half must be of course equals to Pn over 2 because Pn has been bisected. But we already found out that Pm equals to x. So we can write here that Pm equals to x, and from this equation x equals to Pm equals to Mn, we will derive that Mn also equals to x. This is nice with Mn, that is equals to x units in incident according to rule 15. The next step implemented rule 24 in our drawing. So click on rule 24. According to rule 24, first of all, rule 24 is true in any circle. So in the drawing we have a circle. If chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. In the drawing we have a circle. This is chord AB that intersects with chord CD at point O. This drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can definitely implement rule 24 in our drawing. Why? Because in our drawing we have chord AB, that is the diameter of the big circle. Chord AB intersects with chord Pn at point M. Again, chord AB intersects with chord Pn at point M. So all the requirements of rule 24 are satisfied, and therefore we can implement rule 24. And again, if you found out that our drawing we have chord AB intersects with chord Pn at point M. So all the requirements of rule 24 are satisfied, and so we can implement here rule 24. According to rule 24, the following equation is true, that AM times MB equals to PM times Mn. Again, AM times MB equals to PM times Mn. And again, according to rule 24, the following equation is true, that AM times MB equals to PM times Mn. We already found out that AM equals to 4 minus x, MB in total equals to x plus 6. Again, AM equals to 4 minus x, MB in total equals to x plus 6, and it is equals to PM, that is x, times Mn, that is x. So in total PM times Mn equals to x times x, that is x squared. So in total we shall find out that 4 minus x times x plus 6 equals to x squared. Here we open the brackets of this expression. If I found out that 4 minus x times x plus 6 equals to 4 times x, that is 4x. plus 4 times 6, that is 24, minus x times x is minus x squared, and minus x times 6 is minus 6x, equals to x squared. So in this equation we have 4x minus 6x, that is minus 2x, plus 24 minus x squared equals to x squared. So in total, minus 2x plus 24 minus x squared equals to x squared. Here we added x squared to the equation, and finally found out that x squared plus x squared equals to 2x squared. In this side of the equation, we left only with minus 2x plus 24. So in total, minus 2x plus 24 equals to 2x squared. So again, we found out that so here we added 2x to this equation. After we added 2x, we found out that 24 equals to 2x plus 2x squared. And again, we found out that 24 equals to 2x squared plus 2x. Here we subtract the 24 to this equation, and we found out that 0 equals to 2x squared minus 2x squared plus 2x minus 24. Here we divided the equation by 2, and 2x squared over 2 is x squared, 2x over 2 is x, minus 24 over 2 is minus 12 equals to 0 over 2 is 0. So in total we found out that x squared plus x minus 12 equals to 0. So this is the quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. This general formula, capital A, capital B, and capital C are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus 4 of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus x minus 12 equals to 0, the variable that we are looking for is x. X is the radius of this small semicircle. The coefficient a equals to 1, the coefficient b also equals to 1, and the coefficient c equals to minus 12. The only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x. In this way, we find out the value of the values of x, that is the radius of the small semicircle. So we actually did it, and we actually found out that x equals to minus b. B is 1, so minus b is minus 1, plus minus square root of b squared. B is 1, so b squared is 1 squared, that is 1, minus 4 times a times c. So it is minus 4 times a. A is 1, so minus 4 times 1 is minus 4 times c. So minus 4 times minus 12 is plus 48. So in total, minus 4 times ac equals to plus 48. So inside the order we have 1 plus 48 over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, we should find out that x equals to minus 1 plus minus square root of 1 plus 48 is 49 over 2. The square root of 49 is 7, so in total we should find out that x equals to minus 1 plus minus 7 over 2. Again, we should find out that x equals to minus 1 plus minus 7 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to minus 1 and minus 7 over 2. Minus 1 minus 7 is minus 8, and minus 8 over 2 is minus 4. So according to the first solution for x equals to minus 4. But because of the fact that x is the length of this radius, the radius of this small semicircle, so x is a length, and x as a length, it must be a positive number. It can never be equal to minus 4, that is a negative number. So we cancel this first solution for x, and we took into account only the second solution for x. The second solution for x is as follows: x equals to minus 1 plus 7 over 2. Minus 1 plus 7 is 6, and 6 over 2 is 3. So the second solution for x equals to 3. That is to say, the radius of this small semicircle, x is equals to 3 units in its length. Our task is to find out the area of this green shape. From the drawings, it's very easy to see that the area of the green shape in total must be equal to the area of the big semicircle minus the area of this small semicircle. Okay, again, the area of the green shape in total must be equal to the area of the big semicircle with radius 5 minus the area of the small semicircle with radius 3. So the area of the big semicircle equals to pi r squared over 2. R is 5, so it is pi times 5 squared over 2. Once the area of the small semicircle, the radius of the small semicircle is 3, Therefore, they have the small of the small semicircle must be equal to pi times 3 square over 2. In the numerator of this expression, we have 25 pi over 2. In the numerator of this expression, we have 9 pi over 2. 25 pi minus 9 pi is 16 pi. 16 pi over 2 is 8 pi. So in total, we have this green shape, that is the area that we are looking for this question. This is equal to either 8 pi square units inside, so in terms of numbers, they have this green shape is equal to 25.13 square units inside. Okay, thank you very much.